The WOW signal. It lasted exactly 72 seconds. On August 15, 1977, astronomer Jerry Amon was reviewing printouts from Ohio State University's Big Ear radio telescope when he circled a sequence of alphanumeric characters and wrote WOW in the margin. The signal hit at 1,420 megahertz, precisely the hydrogen line frequency that scientists had long predicted an intelligent civilization might use to broadcast. It was 30 times stronger than background noise. It came from the direction of Sagittarius, and then it was gone. Amon and his colleagues spent years trying to find it again. Hundreds of follow-up observations. Nothing. The pivot that changes everything. The signal had all the hallmarks of extraterrestrial origin, but it has never repeated. In 2012, a team broadcast a response toward its source. No reply has come. The WOW signal remains the strongest candidate for intentional alien transmission ever recorded, and nobody knows what sent it. Fast radio bursts. Imagine a flash of radio energy that releases more power in a millisecond than the sun emits in 3 days. That is what astronomers first detected in 2007, when Duncan Lorimer and his student David Narkovich were reviewing archival data from the Parkes Observatory in Australia. The burst had already happened in 2001. They just hadn't noticed it yet. These events, now called fast radio bursts or FRBs, come from billions of light years away. They last less than a heartbeat. For years, nobody could explain them. Then came the pivot. In 2020, one was traced to inside our own galaxy, originating from a magnetar, a neutron star with a magnetic field so intense it warps space. That single detection collapsed dozens of competing theories overnight. But most FRBs still don't match that profile. Some repeat, some don't. The source catalogue keeps growing and the explanations keep multiplying. The Perytons. For years, the Parkes radio telescope in Australia kept catching strange millisecond bursts. They looked almost exactly like fast radio bursts. Scientists were excited. Then a graduate student noticed something odd. The signals only appeared during business hours. That detail should have been a red flag immediately. An investigation in 2015 revealed the culprit was a microwave oven in the observatory's break room. When staff opened the door mid-cycle, it leaked a burst of interference that mimicked a deep space signal with alarming precision. The Perytons, as they had been named, were entirely terrestrial. The lesson hit hard. Every signal detection program now runs aggressive radio frequency interference screening. The enemy pressure here was embarrassment, and the collapse of a years-long mystery into something almost comedic. But it forced the field to build better filters, and it made every future detection more credible by comparison. The Lorimer Burst. Before FRBs had a name, there was just one. Duncan Lorimer's 2007 discovery of that archived 2001 pulse was so anomalous that the broader scientific community initially resisted it. One burst, no repeat, no confirmation. Some argued it was instrument error. Some argued it was atmospheric. The debate ran for years. What made the Lorimer burst specifically significant was the dispersion measure. The way the signal's frequencies were smeared told scientists exactly how much matter it had passed through, implying it had traveled across an intergalactic distance. That was the proof of concept. It said something out there was producing bursts powerful enough to cross billions of light years and still be detectable. The crackdown on skepticism came in 2013, when 4 more bursts were confirmed from the same dataset. The Lorimer Burst became the foundation of an entirely new field of astrophysics, the Bleien Observatory Candidate. In 2016, a team monitoring a sun-like star called HD 164922 using a radio telescope in Switzerland picked up a narrowband signal that briefly looked like it might be artificial. The star sits about 72 light-years away. The signal appeared at a frequency that didn't match known natural sources. The team was cautious, almost painfully so, which was the right call. They ran follow-up observations. The signal didn't reappear. Cross-checks suggested terrestrial interference. But the episode illustrated the brutal daily mechanics of SETI work. You get a candidate, you suppress excitement, you verify, you fail to confirm, you move on. The cost is psychological as much as scientific. Years of listening for one moment that may never come. And yet the protocols built around that discipline are exactly what would make a real detection credible if it ever happened. The 1977 Ohio State alien transmission attempt. Here's a case that runs in reverse. In 2012, a team led by Arecibo-connected researchers transmitted a response to the WOW signal's coordinates. The message contained prime numbers, mathematical sequences, and basic biological information about humanity. The target was roughly 2.0 HU SCO, a region in Sagittarius. The pivot is uncomfortable. We don't actually know if we sent it to the right place. The WOW signal's exact origin was never pinpointed with precision. We may have broadcast into empty space, or we may have sent a message towards something that has no idea what radio is. The enemy pressure here is philosophical. A segment of the scientific community argues we should never transmit at all, that announcing our location to an unknown sender is a catastrophic risk. Stephen Hawking said it publicly. The debate has not been resolved. FRB 121102. This one repeats. That single fact made it the most studied fast radio burst in history. First detected in 2012 at the Arecibo Observatory in Puerto Rico, FRB 121102 fired again and again hundreds of times. That repetition allowed astronomers to localize it precisely, a dwarf galaxy about 3 billion light-years away. Inside that galaxy, it sits near a persistent radio source, possibly a magnetar, embedded in a dense plasma environment. The pattern of its bursts isn't random. It cycles, active for roughly 90 days, quiet for 67, then active again. Nobody fully understands why. The pivot is that periodicity. A natural magnetar shouldn't keep such a schedule. Some researchers have proposed the environment around the source modulates the signal. Others haven't ruled out stranger explanations. The crackdown on wild speculation has been constant, but the mystery of that clock-like rhythm has not been explained away. The alien megastructure star. In 2015, citizen scientists working through the Planet Hunters project flagged a star called KIC 8462852, later nicknamed Tabby's star. Its light dimmed in ways that broke every existing model, not the smooth periodic dip of a planet passing in front. These were irregular, deep asymmetric drops in brightness, sometimes blocking 22% of the star's light. A planet can't do that. Dust clouds were proposed, comets were proposed, and then astronomer Jason Wright publicly raised the possibility of an alien megastructure, a Dyson sphere under construction. The media erupted. Follow-up observations found the star was also slowly fading over decades. The pivot came with infrared data. The dimming pattern matched fine dust, not solid structures. The megastructure hypothesis collapsed under its own weight, but Tabby's star still dims in ways that don't have a clean, fully accepted explanation, and it remains one of the strangest objects in the Kepler catalogue, the BLC1 Candidate. In April 2021, The Guardian reported that astronomers at the Parkes Observatory had detected a narrowband signal near 982 MHz appearing to come from Proxima Centauri, the closest star to our Sun at just 4.2 light-years. The project was called Breakthrough Listen. The signal was internally labeled BLC1. The team sat on it for months, running verification. The pivot was the conclusion. It was almost certainly interference. The frequency matched, signals produced by human technology, and the pattern didn't survive the tests designed to distinguish sky sources from ground sources. But the process was exactly what rigorous SETI looks like: detection, suppression of excitement, months of verification, honest public reporting. The cost was a wave of premature media coverage that outpaced the science. The legacy is a cleaner protocol for how future candidates should be disclosed. The Sagittarius A star radio flares. The black hole at the center of our galaxy doesn't stay quiet. Sagittarius A star periodically releases intense bursts of radio and infrared radiation that have been detected and studied since the 1970s. These aren't signals in the communicative sense, but they are signals in the most literal one. Information encoded in electromagnetic radiation arriving from 26,000 light-years away. The flares spike unpredictably, sometimes brightening by factors of 75 within an hour. In 2019, astronomers recorded the brightest near-infrared flare ever observed from SGR A star. The cause is still debated. A star called S2 passed close to the black hole in 2018, and some researchers think that passage disturbed surrounding gas. The pivot. Studying these flares has taught us more about black hole feeding mechanics than almost any other observation. The enemy here is the galactic center itself, so dense with gas and dust that only radio and infrared light can escape it. The SETI at Home Anomalies. For 21 years, the SETI at Home project distributed radio telescope data from Arecibo to millions of personal computers around the world, using idle processing power to scan for patterns. It generated a ranked list of candidate signals worth following up. The top candidates had names like SHGB02+1-4A, a signal detected 3 times, narrowband, drifting in frequency as if it came from a transmitter with a different rate of planetary rotation than Earth. It was never confirmed. SETI at home shut down active distribution in 2020, citing the shift to more efficient centralized processing. The pivot is what the project actually proved. Not that we found a signal, but that distributed human infrastructure could meaningfully contribute to scientific search at scale. The cost was 2 decades of raised and dashed hopes. The legacy is the architecture it inspired for citizen science computing worldwide. The cosmic microwave background. This one isn't a message, it's a fossil. The CMB is the oldest signal in the universe, a faint glow of microwave radiation left over from 380,000 years after the Big Bang, when the universe first cooled enough for light to travel freely. Detected accidentally in 1965 by Arno Penzias and Robert Wilson at Bell Labs in New Jersey, they initially thought the noise was pigeon droppings on their antenna. It wasn't. It was the echo of creation itself, arriving from every direction simultaneously at a temperature of 2.725 Kelvin. The pivot is in the tiny fluctuations mapped by the COBE, WMAP, and Planck satellites. Those variations are the seeds of every galaxy, star, and planet that ever formed. The CMB is the deepest signal ever detected, and it carries the blueprint of the entire observable universe inside its noise. The universe has been broadcasting since before there were ears to hear it. Some signals are natural screams from dying stars. Some are echoes of the first light. Some are still unexplained. And a handful, just a handful, refuse to be explained away no matter how many times scientists try. What we haven't found yet is a signal that unambiguously says, "We are here, we made this, find us." But the search has only been serious for about 60 years. On a cosmic timescale, we just turned on the radio.